Can you hear me? Can you hear me? Good, right. So welcome back to this session, this really fun session. So who wouldn't like to be entertained? Who wouldn't want to have a great health? So this session is about IUI, who can entertain you and give you a great health. So our first paper is called the Sleeve AR, Augmented Reality for Rehabilitation Using Real-Time Feedback. Mauricio, right?
Mauricio, yes.
Mauricio will give, you from Portugal?
I'm from Portugal, yes.
Right, so he didn't even write down his affiliation. Anyway, we'll give you the first talk. Go ahead.
So, good morning to you all. As I said, my name is Mauricio, and I'm here to talk about our research that we are really excited about, and it has great results. It's called Sleeve AR, Augmented Reality for Rehabilitation using real-time feedback. First of all, after an injury, physiotherapy plays an important role in the patient's recovery. Patients need to be prepared to learn about their condition. They must know about what kind of exercises are necessary to achieve a successful recovery. And of course, that in clinics, there are professionals that teach and supervise. But it is also required for the patient to repeatedly perform rehab exercises at home. Without professional supervision, this can be boring, and patients can fall away from the correct way to perform the exercises, leading to a really poor recovery, or even worse, when badly executed, people can injure themselves even further. Is it true that in some cases, instructions are given in the form of pamphlets or brochures, or even in video, but without proper feedback, no one knows if they are doing it the right way? That's why we believe that automation of the procedure is a real good idea, and augmented reality can definitely help with feedback. Augmented reality is here to stay, and not only for entertainment. There are lots of research using augmented reality, and it's also starting to appear great commercial solutions with applications in engineering, military, and health. Therefore, augmented reality can deal with the issues of unsupervised rehabilitation and movement guidance. Tang et al. Proposed an approach that overlaps 3D information onto two mirrored streams of video showing the patient's movement. Unfortunately, this means that patients must be focused on their attention in two different video feeds, which can be tricky. Anderson et al. Proposes an approach that also overlaps information onto the mirrored stream video of the user. And there are also projection mapping techniques applied to rehab. With Light Guide, Sodi et al. Demonstrated that information can be projected onto the patient's own limbs to guide them into doing certain pre-programmed movements. So, Sleeve AR, it's our approach for rehab movement guidance that uses real-time feedback information projected onto a sleeve, on the arm, and also additional information is projected on the floor. All in the same field of view, patients can perform the prescribed exercises while perceiving if they are doing it the right way. And if not, they can adjust. Our approach builds up from the related work and moves it further. The patients can learn, improve, and precisely replicate prescribed movements. So with Sleeve AR, we set our goals with the knowledge that appropriate feedback do help to effectively guide patients during unsupervised rehab exercises. In short, our key contributions are precise movement guidance for unsupervised rehab with projected augmented reality for error feedback in real time on the patient's own limbs, transforming 3D arm positions into 2D floor, into the 2D floor plane. And also, we achieved a method to compare two movement sequences. So, getting it into more details. The sleeve was made with a white cloth to display the projected feedback, with straps to not move around, and 3 motion capture rigid bodies were attached so that we could track in real time the position of the arm. As I said, we opted with infrared motion capture cameras for precise user tracking, and a short throw projector was attached to the ceiling, facing downwards, to cast the visual feedback on the floor and on the sleeve. For this research, we focused on the upper limb exercises, and Sleeve AR is able to track and guide through different permutations of those exercises, either using the right arm or the left arm. Our approach features 3 distinct stages. First, an health professional prescribes the exercise by recording it. Then the patient can use the recording to actually reproduce the exercise with accuracy. And finally, Sleeve AR offers a review about the resemblance to the original recorded exercise. So to start, actually, is it moving? No. Okay, it's not moving. It's a video. So to start the exercise, first the patient needs to position the arm at the starting point of the pre-recorded movement. This is done by dragging that dotted circle on top of the colored one. We transform the 3D arm positions into the floor plane so that the arm can move the dotted circle around. Simply putting it, moving the arm up, circle moves away, and down, the circle gets nearer to the user's body. Once in position, the patient can start the exercise and an alarm sound is released. During the exercise, the movement's path is rendered on the floor, and the patient runs through that path by following the circle that only advances when the movement is done the right way. So the patient must position their arm using the same technique used for the initial position. As you can see, everything is going well since the arm feedback shows all green. But when the movement is not done well, the arm starts to fade from green to red, and the patient is able to see the color changes in real time, and then he can adjust the movement. We divided the arm into 2 segments. The feedback is shown for each segment so that the patient can perceive errors in the flexion and extension of the arm. Also, a progress circle acts as a widget that informs where to rotate to. Finally, when the exercise is finished, the patient is complemented with a performance report that shows how well the exercise was performed. A representative score is shown, and on the right side, both of the pre-recorded and performed exercises are rendered to better show the difference between the 2 paths and the parts that need improvement. Both the real-time feedback and progress reports are calculated in real time by the degree of similarity between the 2 signals. So, how do we compare both movements? They surely are not equal. Because people came in different sizes and proportions, and surely the patient has a different body structure from the therapist. And also, the therapist and the patient's movements differ in rhythm and speed. To resolve these issues, we employed the dynamic time warping algorithm that intelligently can return that degree of similarity between 2 temporal signals that surely differ in time and speed. So we apply the dynamic time warping algorithm not to the 3D positions of the arm, but to the normalized vectors of the movement, and with this, Sleeve AR returns the degree of similarity and displays the performance review. So we decided to evaluate our approach by comparing it not to the pamphlet or brochure approach, but to a video approach. where the user learns about the exercise by looking at it and acts on it in real time. Our methodology includes an introductory stage where participants were greeted with an explanation of the test and then were asked to perform both approaches. In the end, they are all asked to fill up a questionnaire with user preferences questions using a Likert scale of 6 values. There were 18 participants with an average age of 26, and one of them was an invited health professional. The performed tasks were 5 exercises that combine in a sequence permutations of the presented rehab exercises. This is the second one, where the test participants were asked to reach the initial position, then move backwards, then up, and then forward. As for results, we applied the Wilcoxon signed ranks test to all responses from the questionnaire. Participants reported that they had no problems performing the exercises, both in SleeveAR and with a video approach. Although users reported that seeing if the arm was in the wrong position is easiest using our approach, since we identified a significant statistical difference using the Wilcoxon signed ranks test. This suggests that it's really useful to be constantly aware of the state of the rehab movement. Participants also reported that it was easy to perceive the feedback information. In general, people liked the novelty of SleeveAR, but reported that they were confident that their performance were great in both approaches. But the dynamic time warping values suggest that actually our approach do achieve better results, more similar to the pre-recorded ones. We applied a paired T-student test to the data collected for each exercises on both conditions to assess the performance of our proposed solution under the null hypothesis, which stated that SleeveAR and video observation, no, I'm lost. So under the null hypothesis, which stated that SleeveAR and video observation averages were similar. Indeed, for all exercises, the computed p-values were lower, which invalidates the null hypothesis, showing that the dynamic time warping values are lower on average for SleeveAR than the video observation. Also, focusing on SleeveAR results, the average dynamic time warping results from 3 trials executed. We can all see the improvements on the user's performance in just a small number of repetitions. Not only the average dynamic time warping values became closer to the original, the pre-recorded one. Okay, the pre-recorded one. These improvements on successive repetitions are statistically meaningful. A T-student test indicates the null hypothesis that the performance would not increase with repetitions. So to summarize the results, users were convinced that they performed great in both approaches, even reporting that SleeveAR makes it easy to see when we are doing something wrong. We reached this conclusion using the Wilcoxon signed ranks test, but actually the t-test analysis suggests that users achieved better results with our approach. So we also took the opportunity to interview the therapist that we invited to do the evaluation test. She said to please extend the prototype to full body. She also stated that systems like this could be important for remote progress reports while patients are at home. And finally, rehab gymnasiums could be fully equipped to support multiple patients performing rehab exercises simultaneously while being supervised by fewer therapists. So to conclude, our motivation comes from the knowledge that unsupervised rehab can be dangerous. So we proposed a precise movement guidance approach using augmented reality, and the results show that people can effectively replicate the previously recorded rehab exercises prescribed by the therapist. So, thanks for your attention. This concludes my talk, and I reserve the remaining time for questions. And there's a demo video of the actual prototype.
Question? Yeah. Go ahead. Yeah.
Can you hear me? Yeah. So I have a question regarding the setup of the rehabilitation environment. To what extent is it hard to repeat the same settings between, different instances?
It's not that hard, although the OptiTrack.
Like I guess you need to
tracking
position
system is quite
the
expensive.
projector and the camera and the patient himself. All needs to be relatively positioned in a consistent way, right?
Yes. In this prototype, yes.
Okay, so then the following question will be: have you considered using augmented reality glasses instead of this kind of external setup?
Yes, we did.
Okay.
So augmented reality glasses have yet a limited short field of view. So
Also the floor.
yes, of
Okay.
course. So we believe that in 5 years, projecting on the floor or glasses, it's really the same. We opted to project, so it was easier.
Well, I mean, eventually you would want my grandma to be able to use it, right? And at home. So
Yes, we'd like that.
okay.
Hi. I have 2 questions. By the way, congratulations for your work.
Thank you.
The first question is that I'm working in the same field, in rehabilitation robotics, actually. And have you considered first the personalized individual's physical characteristics in your virtual environment? For example, the difference, as you said, there are different characteristics between the
Yes.
length and the
Yes.
height of the person. So does your system need a calibration process first in order to adjust the amount and the position of this target?
No, it does not need no calibration.
Okay.
It just uses relative positions.
Alright.
And the dynamic time warp algorithm can deal with the different proportions since we just compared the vectors, the normalized vectors of the movement, of the 3 joints.
I see, yeah. But it would be nice to have a phase calibration in order to understand in the range of motion of the user, actually. That would be just a suggestion for you. And also the second question is, does this leave device, because you want to apply this in a home-based rehabilitation, so have you considered provide some feedback to the user if he's doing well or not an exercise?
So we do provide a review at the end of each exercise.
Yeah, but this is a feedback about the result, the performance results.
Okay, yes.
But do you provide any haptic feedback? I mean, any external forces, or do you plan to do something like this in the future?
Yes, we do plan to explore haptic feedback. We thought about that, but the prototype, as you can see, seems to do a really good job.
Good, of course.
And we didn't see the need to add more stuff to the
Exactly.
sleeve.
All right. Thank you very much.
Thank you.
You have a quick question or just a
I'll
very
make it
quick
quick.
one?
I'll
Very
make it
one,
quick.
right.
Hi, Peter Hadawi from Mahidol University. Yes, I'm curious about the assessment and feedback. So you have this nice assessment. Is there any way to, or have you thought about how you might provide feedback to the person to help them to carry out a motion if they didn't carry it out properly? And second of all, have you also looked at gathering data over time to sort of do some diagnostics as to what there may be some underlying physical problems preventing somebody from carrying out a motion?
Okay, outside the simple movement, you're talking about after and before the exercise. So
Well, I'm thinking of, one is the exercise. If it's not done properly, you say, okay, here you didn't do it properly, but then how can you help them to do it properly? And second of all, if you're carrying out several exercises over time, you may be able to recognize that there's some underlying problem that's preventing them from carrying out a motion properly.
That's
Actually,
interesting.
I have to interrupt this. I'm sorry, because we have a very tight time right now, because at 12 o'clock, there's going to be alarm, fire alarm kind of testing. So I want to make sure the last speaker. So I kind of take offline, please, right? So let's get the second speaker, please. Yeah. So our second speaker will be Tamayasu Nakano. He's going to talk about the playlist player interface using multiple criteria to change the playback order of a music playlist. Go ahead.
Hello, everyone. My name is Tomoyasu Nakano from AIST Japan. Today, I'd like to talk about playlist player, which is an interface to change a playback order of a music playlist. Music playlist is a standard tool to listen musical pieces. Typically, playlists can be sorted based on one of several criteria, such as song titles, artist name, album name, ratings, and playlists can sort by random order to increase freshness of the playlist. In contrast, we propose tabular type visualization as an extension of the standard playlist. These 9 properties are extended, and these are derived from audio and from web. I'll explain them. I first explain about the acoustic characteristic, vocal gender, and beats per minute. To estimate vocal gender, we first estimate male-female probabilities of vocalists of songs. We first extract vocal signal from music audio and used probabilistic SVM to estimate the probability. Blue rectangle means male, and female means a red rectangle. And then we estimate beats per minute, BPM. We first estimate beats by using Songo, and then we estimate BPM by computing the median value of the time intervals between individual beats. And then I explain about musical commonness and social commonness. Musical commonness is a kind of similarity between a song and a set of songs. This means a song having higher commonness is similar to songs of a playlist. In other words, it means typicality. Musical commonness is represented by green circles. In this case, Lose Yourself by Eminem has low commonness in this playlist. We focus on vocal timbre, musical timbre, and rhythm of as a musical commonness. And final, we estimate social commonness, which is artist-level social relationships discovered from Wikipedia. We used related entries and categories. Related entries are words which have a link with another entry on Wikipedia. And categories like that, it's kind of tag. So playlist player have 9 properties like that, and these can be used as sorting criteria. We have 4 ways to sort. One is ascending order, and second is descending order, and random order, which means all songs are ordered alternately with regard to the selected properties. And smooth order is this means all song transitions are smooth, including a transition between top and bottom songs. So playlist player can sort a playlist in multiple ways, sorting by 4 ways with 9 properties. In addition, 2 or more properties can be integrated to use as sorting criteria. I can show the video demo. We use vocal gender as a sorting criteria, descending, ascending, descending, random order, and smooth order. In addition, 2 or more properties can be integrated. In this case, vocal gender and BPM can be used as sorting criteria, and the three property are integrated. So I'll explain about implementation. To realize reordering using multiple criteria, we first estimate Euclidean distance matrix based on all properties among songs. And then we estimate a one-dimensional vector by applying principal component analysis to realize ascending order, descending order, and random order. And smooth transition is estimated by solving the traveling salesman problem, like that. So I talk about evaluation. We asked 7 users to use playlist player for 20 minutes. There are many comments. We picked up some comments. As a positive comments, which is capabilities and potential of playlist player, helpful for finding new songs similar to favorite songs, and the smooth order is suitable for background music. And the random order gives fresh listening experience. And then negative comments as limitations. There is too much information for casual listening, and the reordering by integrating is a bit more complex. And we also evaluate the accuracies of estimation method. We use 19 songs and evaluated, but please read the paper in detail. We conclude. So how to listen an exist playlist, which is originality of playlist player. Previous research mostly focused on playlist generation and visualization. So feature directions, some visualizations and functions should be improved, and to utilize context by user modeling. Thank you. Thank
So
you.
how did you decide those kind of 9 criteria of this one? How did you decide to use them?
Yeah, one was, so we can estimate, and the vocal gender is, we decided them based on the effectiveness of the sorting. So vocal gender is very effective to decide the playlist or sorting order, I think.
Any other questions? Okay, so let's thank the speaker.
Thank you. Sorry.
Okay, so let's welcome our third speaker. And the title of this paper is called Remind Me, an adaptive recommendation-based simulation of biographic associations. And Dominic will be presenting the paper.
Okay, hello, my name is Dominic. I'm here to present current work from our group in Würzburg. With my colleagues, we did this, Jean-Luc Legras, Dennis Wiebusch, and Marc-Erich Latoschik. Our work is about, in the general field, in dementia care. First, to give a motivation, the context of our paper is the general health issue dementia. There's especially some researchers estimate that the number of people having dementia in the worldwide will grow and double every 20 years due to a rise in life expectancy, and this will have an impact especially in low and middle income countries. One popular intervention fostering the well-being of people with dementia is reminiscence therapy. Just to give you a glimpse, in reminiscence therapy, the therapist is is using items, personal items of the human with dementia to enforce a sense of identity and to facilitate memory activation, and hereby to improve the well-being and to induce positive effects. The challenge hereby is that it's like a treasure hunt. So which items are the items that have the capability to have a positive impact? Yeah, and our question in this research I will introduce here is how can we help using a recommender system so that the therapist might have a helping system on hand to choose items for using in reminiscence therapy. Just to give you a glimpse, here's 2 pictures of typical reminiscence therapy sessions. So normally people are using photo books or items in groups or alone with a therapist, and just talking, trying to engage. And on the technical side, the restrictions for us, we had to ensure that we had the restriction that we can only use a very small amount of data, and we cannot use typical big data approaches due to a very individual setting for each patient. And furthermore, we could not, or we had to try not to distract the sensitive interpersonal setting within the reminiscence therapy, because this is one of the most important things here. This is an interaction. So if we use technical devices, we have to be very careful. Yeah, and so we tried to reduce the required interaction with the device to a minimal amount. Okay. I will look at time. Okay, here, just to give an idea of our system, we had a tablet-based system, and it's just using images. And the only thing that the therapist and the patient can do here is just to select images. He can scroll left and right and select images. And the selected images is big on the left side, and related images selected by our recommender system are recommended on the right side. On the technical side, we realized this by an updating distance measure. This is iteratively updating. Okay. I will make this very short. You can read this in the paper. What we use on the technical side is that we consider each photograph as a stimuli, and we can define a set of semantic features on this stimuli, and for each feature we can define distance measures that make somehow sense. Then we have this very diverse set of distance measures. We normalize these measures, and then we on the second step I'll show you later. And then we try to by the way we combine this distance measure to reflect the current mental state of the patient, and maybe the current activated schema that is activated, and hence by estimating this schema we try to give or to recommend items that are suitable for this conversation at the moment. Okay. Okay, thank you. Okay, so here just a roughly explanation what is happening. The details you can see in the paper. So we consider this interaction, selecting a new image as a graph traversal, and in each iteration the actual distance to the other items is updated. How do we do this update? So we define a set of arbitrary these semantic measures that are given, and in the current step we just compare and these measures, and we weight these measures according to their similarity to the selected item. In a further step, we to have the time dimension in this current measure involved, we consider a certain amount of previous iterations. We combine these these weights to a total weight. Again, combine these in a linear combination, a weighted sum, and this gives us the current distance measures, the current distance measures we use for recommending new items. Okay, that's in words. Okay, this is our work in progress. So where are we standing, where are we going? At the moment, yeah, we had a pre-evaluation, but only with a non-clinical subjects, participants, sorry. Yeah, this we had encouraging results, but we didn't yet have the clinical participants. At the moment, we have the problem. If we want to evaluate the system in the clinical setting, we need authentic content, and so we are trying to use collaborative work ideas for gathering semantic knowledge and authentic resources, and to start actually a field evaluation of the system. Okay, so that's it. Thank you. And questions?
I guess I scared you guys. Go ahead, ask.
It was fascinating work. So I was wondering, so the patient is the one who chooses the first picture, right? When you were showing the selection of the initial picture is done by the patient, is that?
So actually, we don't really put a focus on how to initiate the system. So when we design, at the moment it's quite arbitrary. So we have a random picture, and so you can scroll on the left and right and just select and just if the system starts when you repeatedly select items, then it uses this knowledge to recommend further items.
But who does the selection? The patient. When you say repeatedly select.
Okay,
items.
sorry. Yeah, so the selection actually, this is, I think mostly it's done by the therapist, but it's not mandatory. So maybe you can imagine like that the tablet is lying on the table, and they are talking, and then maybe the patient is touching an image, or the therapist. So yeah.
So I was just wondering, in general, when you generate recommendations for new pictures that are related to the one that was selected, how do you understand, is the system capable to understand whether that picture is the right one, given the patient's reactions? I understand there is a therapist there, but if therapist was not there, how would the system assess whether the selection was effective or not? Do you capture things like, because maybe the patient is not capable of verbalizing if the cognitive impairment is high, but there would be other things that are cues that the system could trace to see if the picture is good. So do you have any thoughts on that?
Yeah, this is very interesting. We are quite thinking about this topic. It's not actually contained in this work now, but actually we're thinking about ways how the system can get explicit and implicit feedback without disturbing this interactive situation too much. Yeah, but this is a very very interesting topic. Yeah, thank you. Yeah.
Okay, I'm going to ask a quick question. You can switch, right? So currently, I guess you haven't taken into consideration the individual differences between the patients, right? So, for example, some patients may be better triggered by images, and other patients might be better triggered by sound or music or other things happening in their life, right? Have you thought about that?
So no, at the moment there's the individuality of the patient is only reflected by the selected distance measures and by the items themselves, but the system does not adapt inherently to individuals. Yes.
Okay,
yeah.
great. Okay, thank you.
Thank you very much. Yeah.
Okay, we're moving along very well. So let's come to our next long paper presentation. It's called Empirically Studying Participatory Sense-Making in Abstract Drawing with a Co-Creative Cognitive Agent. And Nicholas will be making a presentation.
Hi, my name is Nick Davis. And so overall, this work is about applying this new cognitive science theory of participatory sense-making to try to help influence the design and evaluation of these co-creative cognitive agents. So participatory sense-making is particularly interesting and relevant in this context because it's about how people interact to build meaning in real time through kind of negotiation and feedback. So that's going to help us understand how to characterize collaboration and improvisation with these co-creative agents. So when we're thinking about participatory sense-making, there's a few critical concepts that help guide the design and evaluation of these systems. First being interaction dynamics. So what is the structure of the interaction? How is turn-taking taking place? What's the rhythm and the kind of type of the exchange that's taking place between these two agents that are collaborating, whether they be humans or a human and a co-creative system? Next is coupling. So how does the interaction, are they related to each other? Are they just coupling with the environment? So for example, you can have two agents that are separately in the same environment, but they're actually coupled with the environment itself rather than with each other. So that would be kind of two people drawing on the same canvas, but kind of in different spaces on different activities. Or you can have them coupled with each other and co-regulating the sense-making process, where it's like both agents are mutually influencing the meaning that's being produced, which will lead to a more emergent style of meaning. And that meaning, emergent being that it's greater than the sum of the individual parts. And you can't necessarily predict what would have happened without that coupling and that co-regulation. And so that idea of co-regulation is really critical to this idea of trying to achieve participatory sense-making, which is like the ideal or gold standard that we want to try to achieve with these collaborative co-creative agents. And finally, we consider the flow of experience through time. So what happened in the early part of the improvisation should influence what comes later, and some kind of narrative thread might emerge to connect all these different experiences over time. So these are some of the concepts in the framework that we're using to evaluate the co-creative drawing system that I'll be presenting now. So the system is called the Drawing Apprentice. Some of you might have seen it in the demo session. I'll give you a quick kind of demonstration here just for you to get an idea about what the interface is doing, how it's working and stuff like that. So on this interface here, you can see a few different elements that aren't usually present on a drawing application. We have these voting buttons here, so you can give the agent feedback about how he's responding to you. We also have this agent creativity level that's influencing what types of responses he's going to be providing to you. And so as I start to draw here, he's at a very low level of creativity, so he's just going to kind of very closely imitate what I've done. So kind of just small translations and kind of mimicking what I've done. And I can give him feedback, okay, that was okay, agent. And then I can turn the creativity up. And as I increase the creativity, he's going to transform that input in a more substantial way. So there might be a rotation, a translation involved. But he's still taking that input and adding onto it in a particular manner. And if we crank the creativity all the way up, he's going to analyze that input in a little bit more interesting way and vary it by actually altering that input line and going in there and messing with the individual features of the line and swapping out particular elements. And so this platform, being online, we can collect the data from a lot of different people and continue to improve the system over time. So it's kind of a crowdsourced way of collecting sketch data and understanding how people collaborate in this context. So that's the overall idea of the system, and you can continue to vote and help him understand what types of things you prefer over time. And so the agent will continue to increase his intelligence and understanding of your drawing preferences and trying to coordinate with you as you progress. So as I mentioned, there's these kind of different classes of algorithms. The low creativity is kind of doing small perturbations on the initial input. Medium is transforming with rotations and scaling. And at high levels of creativity, it's more so like a mimicking where you're taking that input and then stretching it and skewing it in a little bit more of interesting ways, accentuating the peaks, and splicing in different things into that initial input line. We have some different drawing algorithms in the pipeline that I can explain more later if you guys are curious, if you're going to ask about them. So we performed a user study to explore what factors were important in determining whether users can make sense of what the agent is doing and how that affected their collaboration. So in this study, we compared an expert human who was behind the scene controlling the agent compared to the actual agent interacting. And the user wasn't aware kind of which one they were interacting with, and they were kind of randomly interspersed. And then after the task, we had a retrospective protocol collection where they would watch the video of their interaction and describe what they were experiencing, what didn't make sense, what did. We had 7 participants, so it's kind of an early study here, all novices. And to analyze the data, we looked at that retrospective interview data, performed a thematic analysis focused on these kind of elements of making sense of the agent, what types of interaction dynamics occurred in that session, and whether or not there was emergent meaning. Was there kind of a back and forth building on the meaning over time between the user and the agent? So I'll kind of go over some of these qualitative findings. First, we have these this is both for the agent condition and the Wizard of Oz condition, which was the expert human, because we were interested in what really mattered to these users. Regardless of whether they were working with a human behind the scenes or working with an agent, what were the things that were critical for them in evaluating their interaction overall? So first, the idea of spatial awareness, which was really important. So they wanted the agent to respect the lines that they had drawn and the boundaries that they had created. So, stay within the lines, color within my lines, don't mess up my lines, or go around the contours that exist. And so that suggested a sense that the agent was actually aware of what they were drawing. Next was a visual similarity. So when the agent's contribution had some sort of visual similarity to what the user had drawn, they could see why the agent drew that. So they could understand the relationship between their turn and the agent's turn. And third was this idea of perceptual logic. So this is kind of an individual subjective sense of why these lines make sense. For example, here, these lines are kind of all 90-degree angles and intersecting, and if you drew a bunch of wavy kind of squiggly lines, that would violate that idea and that logic that was developed in this context. So we can go over a few of the examples from the study of each of these individual qualities. So this is a positive example where the agent was respecting that spatial awareness and kind of going around the contour, and the user ended up giving it an upvote because for that reason, since he was actually kind of seeming intelligent in that respect. And here we have a situation where the agent is actually going outside the lines and not really respecting the initial, the dress that the user had drawn, and so then the user gives a downvote to signify, you're drawing something kind of bad here. Next, the idea of visual similarity. So the user had input this kind of spiral, and the agent kind of translates and scales that spiral. And since it has that visual similarity and it's kind of predictable in its response, the user went ahead and gave an upvote and noted that, okay, now I understand what the agent's doing. I can kind of work with it since I can predict and anticipate what it's going to do. Here's an example where the visual similarity principle is broken. So the user was drawing kind of circles in this circle activity, and they input a final circle, and then the agent draws a line. And so they were like, well, why did it draw a line? Where did that come from? And that kind of deviated from my expectations. And so they gave that a downvote because there wasn't a visual similarity there, and it was hard for them to understand why it would draw that particular thing in this context. Here's this idea of perceptual logic. So the user was drawing squares inside this kind of boat shape, and the agent also is drawing squares. So this is kind of combining spatial awareness, visual similarity, to create this type of logic that the user is going for. And when the agent was agreeing and performing in a similar manner, the user gave an upvote to signify that yes, this is kind of what I was going for. Here's an interesting example where the user had drawn a line inside of a shape, and the agent did a similar action inside of a different shape. So it agreed with the spatial awareness. It's within the bounds. It's visually similar to the contribution, but it was on this spiral. So there's kind of this logic where this spiral is going on. So things related to spiral would have made sense there. But since he took this idea of like a circle within a container and applied it to that situation, it violated what the user had expected. And actually in this condition, they gave a downvote, and in the retrospective interview, they had a strong negative sentiment about that because for some reason they had a strong attachment to that spiral that was like one of their favorite aspects of the drawing, and so they're very upset about that. Mentioned it several times. So here's kind of a comparison overall about what happened in the Wizard of Oz condition versus the agent condition. In terms of making sense of the agent, In both scenarios, the user was able to kind of anticipate and predict what the agent was going to do, and that was good, and that actually seemed to be an important factor in their interaction with the agent, the ability to anticipate and predict, but not precisely predict what the agent is going to do. You still want some variability in there, but without the ability to predict, it was kind of things go a little haywire. Next, in terms of interaction dynamics, in the Wizard of Oz collaboration, there was this kind of co-regulated coupling that emerged where sometimes the user was the leader, sometimes they were the follower, and they kind of went back and forth and exchanged roles. So that's really what we want to see in participatory sense-making, and since this is the human condition, that's kind of what we would expect to see. And in the agent collaboration, we saw more about the user leading and controlling the agent. So since they were able to predict and work with the agent, that's good, but it doesn't go all the way to that co-regulated coupling where there's kind of this exchange of roles over time. And that kind of carries over in the emergent meaning, where in the Wizard of Oz condition, visual ideas were emerging both from the user and the agent, and that was transforming over time in interesting ways. Whereas in the agent condition, the user was more focused on incorporating and adapting to what the agent was doing. So they're trying to bring what the agent was doing into their idea rather than going back and forth. But you still see some element of evolving meaning over time, and even though you're just adapting to the agent. So now I can go about some particular excerpts from their descriptions here in terms of the Wizard of Oz collaboration. Here we see, they're saying that they can anticipate what the agent did and develop some kind of preference through that anticipation when it's violated or not violated. And then in interaction dynamics, they identified a few different types of modes of interaction. There's like me teaching it copies me, or I copy it, or we're collaborating together on the same task. So there's different types of interactions with the agent in that condition. And then in terms of emergent meaning, we see that first, the thing appeared as a flower, and then the agent did something, and then that reminded them of another object, so they extended that, and then the agent added onto it. So it's this idea that was, continuing to evolve over time through the interaction, which is really kind of what we're expecting the gold standard in this situation. And then in the agent collaboration, also the users were anticipating what the system was doing, able to work with that. And then in terms of interaction dynamics, they were mentioning this back and forth, right, and how new things were emerging on the screen and how that was kind of compelling them to want to move forward, which is really what we want this tool to do. We want to creatively engage people and help them expand their creative boundaries through this creative dialogue that's emerging. And then in terms of the meaning that was happening, I did more doodling to see how I could incorporate what the pencil was doing. So they're changing their creative behaviors to explore how that their collaborative partner is interacting with them. So I thought that was quite interesting in that context. So how did the voting fare? Did the people utilize it? Did it help them coordinate with the agent? So people did use it, and it's a good way for us, looking back over the data, to understand in what circumstances they were pleased or displeased. But it wasn't fully understood by the users. One of the reasons is because there was really no feedback in the interface explaining how the votes were affecting the algorithms of the system. And it could also be distracting. So if you're engaged in this creative task and you're creatively immersed, sometimes you might forget to vote, right? So it's almost like if the agent's doing well, then we're not getting the data that we need to help improve the agent. So we have to think about what that means and how to expand upon that. So now with these kind of things in mind, we've come up with some design recommendations moving forward for our individual project as well as others that might be doing this kind of co-creative improvisational collaboration. And so we need to apply the machine learning in a way that's spatially and temporally sensitive. So now it's kind of like you vote, and then the agent learns overall for the entire session your preferences, but really your preferences might change in different regions of the drawing, like that idea of perceptual logic where you're saying in this corner you might be kind of about 90-degree angles, over here you might be about flowy lines, and those ideas and intentions can evolve over time, so we need to adapt to the evolution. Also, we can leverage implicit feedback in the learning algorithms. So one thing is repetition is a strong indicator that the user is actually trying to teach the agent something, either repetition within one turn or across turns. And we can use that knowledge to identify the kind of mode that the user's in. Okay, they're in a teaching mode. We should try to learn this activity and remember it over time rather than requiring an upvote to do that. And when the user is mimicking the agent, that's probably a strong indication that they're kind of coupled together. So if the agent does something, performs an action, and then the user performs a similar action, and we can kind of compare the difference between those two actions in the space that they're operating within, then we should keep on doing that same thing. Keep that coupling going as long as we can until the user breaks it and starts kind of a new activity. And finally, we can disambiguate the voting in some interesting ways. So we can provide the feedback in the UI about what the system is learning from the vote, how it's influencing different learning algorithms, and explore the use of categorical feedback, so providing specific types of feedback about, I liked where you draw, I liked how you draw, the style of the line, and also the content, what you drew in that particular situation. So to conclude, this idea of participatory sense-making is a really interesting theory in cognitive science, and it provides a useful framework to support the design and evaluation of this very novel type of agent that's actually co-creating with users. And in our particular prototype, collaborating with the agent tended towards the user controlling and leading the agent, whereas the Wizard of Oz collaboration included more of this co-regulated coupling, but it gave us a lot of indications as to how to improve that performance with additional iterations of the prototype. And so that gives us encouragement that co-creative agents do have the potential to facilitate this creative dialogue that can lead to emergent meaning and creative inspiration. So that's it. And then if you want to try the Drawing Apprentice for yourself, you can check out this website. You can log on and play with the system. You can join your friends in a room, and multiple people can interact on the same thing with co-creative agents. So it can be human collaboration and human-computer collaboration and all kinds of combinations thereof, and help us gather more data to help improve the system. But thank you for your time, and take some questions on.
Questions?
So you talked about improving performance. How are you measuring performance, and what's your objective function? What does good performance even mean?
Right, so one idea is this idea of the coupling, right? So whether the agent is actually, agent and user are coupled in their interaction. So if the user performs an action and the agent responds, does the user then respond to what the agent did in that scenario? And so are they kind of engaged in this back and forth where all their contributions are contributing to constructing this idea that's being developed? So one way to indicate that is, are they operating within the same space, right? So if the agent does something and the user responds in a similar area, then that's one indication that they're working on the same idea and the user's trying to build off of what the agent is doing, versus if the user goes on the completely other side of the canvas and starts something different, then that could be an indication that it didn't really care for what the agent was doing. So how incorporated is what the agent's contributions into the overall drawing is one indication. Another indication is kind of the voting, but like we said, users might not necessarily use that throughout the process. Additionally, are they drawing more? So compared to a baseline condition of independent drawing, are they more engaged? Are they more willing to explore more visual ideas and creative engagement in that sense?
Hi, great talk. I really want to play with the system now. I'm a little curious about the creativity that you reported. So you had low, medium, and high creativity, and then they have various modifications. So there's mimicking, and then there's transformations. How did you decide what makes a highly creative output versus a medium or a low creative? Is that supported by the voting on the user part, or is this testing, or?
So is it how do we map, what do we determine as high creativity?
Yeah, so I noticed that, for instance, the transformations occur mostly at the level you identified in the algorithm as, say, medium creativity,
Right.
whereas high creativity is more mimicking user behavior with interesting transformations.
Right.
But what is the difference between those two? Did the user say, I believe this is higher in creativity, or is this something
So
you
we made that
determined
mapping. It was a design decision on our part, and really it's about how much manipulation the agent has to do to that input in order to arrive at the result. So the transformations are very simple kind of ways of manipulating that input, whereas at the higher levels of creativity, you're actually having to go in and look at the individual coefficients and stretch and skew it in different ways and accentuating parts of that line. And so it's more work on the agent's part to be able to manipulate things in that way. And the diversity of output coming from the high creativity is much more unexpected. So you'll see lines that don't look as much like the input line. So it's kind of deviation from the input as a measure of creativity, essentially.
All right, yeah, that makes sense. Thanks.
Okay, so let's thank the speaker. now we're coming to our second to last paper. It's also a long paper. It's called The Real World Neural Adaptive and Immersive Virtual Reality Meditation System. And Joka will be presenting the work.
Hello everybody. I'm Ilkka Kosonen from University of Helsinki, and I'm presenting our system, the Neuroadaptive Immersive Virtual Reality Meditation System. Neuroadaptive and Immersive Virtual Reality Meditation System is a bit of a mouthful, so let's take it apart to look at what are the pieces. First, let's dissect it from the end part. Let's look at the meditation because that's the core concept of this. So we are talking about the meditation system, but why a meditation system? It might sound a bit esoteric or even unscientific, but actually there is a ton of research showing that meditation has a wide range of benefits, which I list here. For example, meditation has been used to help against anxiety, stress, depression, etc. Meditation has shown to help concentration, relaxation, creativity, decision making, and so on and so on. It has been shown that meditation not only helps with like mental issues or mental problems, it can also directly help with physiological problems, if you can call them. So in short, meditation has countless of benefits, but why don't we all just meditate daily? I mean, at least I don't, even though I often try. I'm sure that there are plenty of reasons, but I think one big one is that usually meditation demands a kind of secluded, peaceful environment, and in our modern world, it often is not possible for all of us to have an optimal meditation chamber or monastery. So that's where the virtual reality comes. What if we all could enter a perfect meditation environment just by putting on a virtual reality glasses or head-mounted display? This might sound a bit wild, but actually virtual reality-based therapies have been successfully used in treatment of all kinds of disorders outside of this meditation team. So there are research that shows that virtual reality can be used to help in fear of flying, social phobia, post-traumatic stress disorder, fear of spiders, and so on and so on. Actually, one meta-review concluded that these kind of virtual reality-based therapies are more successful than when you try to confront your phobia in the real life. Virtual reality therapies can also help in such things as eating disorders, where patients can work on their self-image with a virtual body. But this virtual reality therapy thing is rather niche. It has been used in maybe by a few professionals in clinical setting due to the hardware basically being rather expensive. But this all might change. As we all know, just this year, many virtual reality devices are coming to the market. Okay, then the third part of the puzzle. Now we went through the virtual reality and the meditation, but what is neuroadaptive here? Neuroadaptive comes from neurofeedback, and neurofeedback is a form of biofeedback, where the brain activity, usually measured through EEG, is used for the feedback. So what does this have to do with meditation? Well, most meditations, there are of course very many meditative practices, but many of them have this extremely important part of self-reflection. If we talk, for example, one of the most famous meditation, what would you call it, techniques, or the mindfulness meditation, the whole point of mindfulness meditation is to become mindful of your bodily and your mental states. And this is pretty much the definition of biofeedback, which aims to make you consciously aware by explicitly feeding back certain unconscious or implicit states. And again, there are lots of past research that show how neurofeedback has been proven to be a useful tool in treatment of various disorders, including these attention deficit disorders, epilepsy, learning disabilities, autism spectrum disorders, and many more. So, if neurofeedback, virtual reality-based therapies, and meditation all have these excellent benefits, why not combine them all into one system? And that's what we have done. Here we have it, the Relavolt system. It might not look particularly relaxing from the outside, but here it's what it looks from the inside. So we have created this tropical island paradise that you can enter to meditate simply by using our system. I'll go into the details of each part shortly. Okay, just a few points about our user study. So to test this system that I just showed, we decided to have a user study. And for this user study, we needed to select a few meditation exercises that are suitable for this sort of thing. There are many kind of meditation traditions. So we used these criteria to choose the meditation exercises for our study. We wanted these exercises to come from the same category of meditation exercises, which is focused attention. I talk about that more later. We wanted that these exercises have been previously studied to at least some degree, so that there is some previous work. We wanted that these exercises would be easy to learn and to instruct novice users, because our test subjects were normal university students, not some monks that we got from somewhere. We wanted that these would be clearly theoretically distinct, and we wanted to have a predictable mind effect, even in short-term practice with novices, so that we could get some sort of an effect even with a single session, basically. And that they were hypothetically more or less suited for virtual reality. Based on these points, we selected two meditation exercises. One is called point focus meditation, and another one is body scan meditation. Both of these are from this same category of meditation exercises called focused attention meditations. Now I just show you quickly what these consist of. So here is a video of the point focus meditation setup. The point here is to concentrate on this point, which is the one lighted circle, and it changes randomly. So your task in this meditation exercise is to keep concentrated on this singular point, and that's it. The second part is the body scan meditation, which is famous in the mindfulness scene. This practice asks you to pay attention to particular point on your body. And you can see in this avatar displayed in the video the part that we want the meditator to concentrate on. Okay, so while these two exercises are seemingly different in many ways, they do share the same basic logic of actively controlling your attentional focus on something specific. That's the similarity between these two. The difference is that in the point focus, the point of focus is external. We want them to focus on this dot in the screen, and in the body scan, you want to focus inside your own body, let's say your knee. So in this case, whether the point of focus is inside or outside the virtual reality. Okay, so now we have discussed the meditation part and the virtual reality part, then more details about the third part, which is the neurofeedback. So for neurofeedback, we used a 6-point EEG recorded from these 6 standard locations. It's shown on the screen. We did a frequency-based analysis, and we based the neurofeedback on 2 different signals. One is this theta activity and the alpha band activity, from these 6 electrodes. I unfortunately don't have time to go into the details of each. The details are in the paper. But anyway, in case there was increase in the power of the theta band, so this 4 to 6 hertz activity, then you would be able to float inside the virtual reality. And this would be considered to be concentration. This comes from the literature. It has been shown that the theta correlates with concentration. On the other hand, the alpha band correlates with relaxation, and this will increase the opacity of the energy bubble surrounding the user. I don't know if you remember in the first video I showed there was this big bubble. So the user is surrounded by this energy bubble, and the opacity of that bubble changes based how relaxed you are based on the alpha band activity. Here we have videos of those. Here we have the floating effect. This video is in double speed so that we can see in limited time the effect. We can see that there is this floating effect, which is directly connected to the meditator's theta band activity in those 6 electrode locations. And here we have the alpha band relaxation, which will increase the opacity of the energy bubble, which basically here comes out as this kind of fogginess, the fog. Of course, you have to remember that in the actual scenario, the user would be wearing a virtual reality headset, so they could turn their head. So we are now kind of, for this video, the camera is fixed. Okay, so to see whether this actually works, we did a user study with 43 participants. We basically had 6 conditions. We had 2 meditation types that I described, the point focus and the body scan. We had 2 types of mediums. We had the virtual reality glasses, and then as a control we had the normal monitor screen, and 2 adaptation settings, which just means that we had neurofeedback or no neurofeedback. Of course, this 2 by 2 by 2 would have 8 different combinations, but we omitted the neurofeedback without virtual reality simply because the study length was already going to 3 hours. Each of these 6 exercises lasted about 10 minutes. After the 10-minute meditation session, they filled out questionnaires and then did this sort of working memory task that was just there to kind of reset their mental state, so that they had to make this somewhat bothersome memory task just for that reason. To measure this system, we used 2 questionnaires. One was this ITC sense of presence inventory, and the other one was a meditation depth questionnaire, MEDEC. From the ITC sense of presence inventory, we choose a subset of questions from the full questionnaire, so as to keep the experiment duration reasonable. We had some issues with that. As I mentioned earlier, we had a 3-hour experiment. And then we used the full MEDEC questionnaire. Okay, I think it's clear why we would want to use this meditation depth questionnaire, but what about this presence thing? So presence is a very well-known concept that I think is very well described in this quote. In general, what distinguishes virtual reality from other media or communication system is the sense of presence. Specifically, we argue that the higher sense of presence induced by virtual reality may be used to elicit optimal experiences that will support the process of change. This comes from a paper by Riva et al. Okay, so we measured presence, and what we found is that screen without neurofeedback produced by far the lowest amount of presence. Head-mounted display without neurofeedback was greatly higher, and the best result was neurofeedback combined with the virtual reality. Then about the meditation questionnaire, I have divided in 2 parts. One is about the negative sides, and the other one is positive sides. So this is about the negative sides. The hindrances part of the meditation questionnaire deal with negative feelings associated with the meditation experience. It was measured with questions like, I found it difficult to relax and I felt bored, and the screen condition elicited significantly higher negative feelings than head-mounted display. The neurofeedback was, there was a trend that it was even better than head-mounted display alone, but that was not statistically significant. For the relaxation, which was measured with questions like, I felt well and I became more and more calm and patient, we found that screen, that is the normal computer screen, generated least amount of relaxation, and that was significantly lower than when this system was used with virtual reality glasses, but that there was no real difference between the virtual reality with or without neurofeedback. Okay, so in summary, virtual reality systems can generate higher levels of relaxation and concentration, as well as feeling of presence than just a normal monitor screen. This effect is further increased with the addition of neurofeedback, and that the effect is same for both type of meditation exercises. I kind of skipped that part, but in there we combined the data from both of the meditation exercises because the results were exactly the same for both the point focus and the body scan. In the future work, we are planning to implement a walking meditation. This does not mean walking in the real life, it means walking in the virtual world. Then we are doing something like individually defined alpha and theta band, which is a fact that there are some individual differences in the optimum EEG parameters to at least what frequencies to use. Then we are thinking about a shared meditation space over the net. Oftentimes meditators go to a shared space to have a meditation session. It might be and with virtual reality, it of course would be totally possible to have any number of people meditating in virtually same location. And then there is of course the possibility of including other physiological signals into the setup, not just EEG, but electrodermal activity or heart rate and what are there. Some acknowledgements. We want to thank Academy of Finland, European Commission and Finnish Work Environment Fund. Okay, thanks. Any questions?
Go ahead, yeah.
Thank you for the presentation. Do you mind switching back to the slide which shows the experimental design with the factors that were manipulated?
This one.
So had the user been aware of the manipulation of the biofeedback?
Yes.
So this could be also the effect of their perception of the existence of the biofeedback, right?
That is a good point.
Okay.
And I can't say more about that. That is a valid point.
Hi, I'm Massimo Zancanaro. It was very interesting work. I wonder, you have 33 participants. Did you check whether they were already used to meditation or similar techniques or
yes.
not? And how's the effect of individual differences?
Can I stand on the mic?
Yes, sure.
Okay, so the 43 subjects were normal university students. We did have a background question of how much meditative experience do you have, and if I remember correctly, the answer was that they were all novices. I can look into that if you are really interested. But yes, they were basically novice, normal university students.
Yes, so I'm wondering if there is if the participants are actually learning meditation through this. Are they dependent on the biofeedback, or is there some retention of the skill over time?
That's an interesting point. I'm not sure if they are actually learning anything except the technique is reasonably simple to learn. I mean, if you just think about the mechanics of concentrating on a point, there's not much to learn. So I'm not. I would say that you don't get any sort of like if you want the benefits, you need the system in a sense that there isn't that sort of retention. I'm not sure did I answer it.
Okay, thank you very much. So now we're at our last speaker, and Sarah will be presenting interactive visuals as metaphors for dance movement qualities. Go ahead.
Okay, thank you. Hi everyone, so I'm Sarah Fdili Alawi. I'm an assistant professor at University Paris Sud, and I'm happy to present on behalf of my colleagues and shrink a long paper into 7 minutes. I'll try. So the context of this work is third wave HCI that is much more interested in meaning, expression, culture, kind of a post-WIMP interaction related to emotion, lived experience, engagement, and motivation. And within this third wave HCI, we're interested in things like these. So how to design an interactive system that extracts the essence of this kind of work. And the essence of this kind of work is the movement qualities that are integrated in the dancer's body. And these are movement characteristics that are related to the dynamic of the movement and not the trajectory itself. It is the way we do move and not necessarily the trajectory and the spatial aspects of the movement. So part of this work has been to design an installation called Double Skin, Double Mind in collaboration with choreographer Emio Greco based in Amsterdam. And this installation is for pedagogical purposes. It basically learns to dance students or dancers how to perform 4 movement qualities that have been defined by the choreographer to shape his vocabulary. The first one is the breathing, and it's a progressive extension of the body in a vertical space, going a little fast. The second one is a release of the body weight into the floor, letting it rebound for a certain amount of time. The expanding is a rotational 3-dimensional movement in space that allows you to achieve different directions. And finally, the reducing is kind of the end result where you're moving in a viscous environment as if your movement is evolving in a honeypot. So we designed Double Skin, Double Mind interactive systems, and that's composed of a camera. We've extracted some movement quality features, and I encourage you to refer to the paper to know how we did that. Then we used some HMM-based recognition system to be able to classify the movement qualities of the dancer into the 4 elements. And based on that, a mapping strategy is actually triggered and allows the visual representation that is based on physical model to have a dynamic behavior that allows the dancer to know what he's doing and what he needs to do to achieve the movement quality. So this is the physical model that we designed, and it's based on a very simple mass and spring system whose presets allow to reproduce 4 behaviors that represent the breathing, then kind of a jumping behavior, an expanding behavior, and a reducing behavior. Again, once the machine learning algorithm recognizes the movement quality, those presets are triggered, but then a mapping strategy that allows that physical model to have the jumpiness of the dancer and the breathiness of the dancer to be triggered as well. So once we designed that interactive system, the questions that we were asking ourselves are, how much of the capacities of that physical model is to generate these dynamic behaviors that could be metaphors of the dancer's movement qualities? And on the user side, what is the experience of that movement quality-based interaction? And what are the exploratory and pedagogical values of these interactive systems? So first, to know whether these physical models could be metaphors of these movement qualities, we run an online questionnaire with people that have been taking the workshop with the choreographer directly and ask them to rate different simulations of the physical model into breathing, jumping, expanding, and reducing. And I'm not going into the details at all. This has been quite a large questionnaire. But the results are that the preset that we developed for double skin, double blind give the best perceived correspondence between the visual behavior and movement quality. And more generally, these mask-spring system, no matter how much we abstract the image of the body, can generate dynamics that can be perceived by a dancer to be similar than their own body's movement qualities. Moving on, so we run also 2 user studies with 2 different populations. One population is the dancers of the company, there's 10 of them, and another population is the students of the Amsterdam School of the Arts. 16 of them took the experiment in which we had 2 interaction modes. One interaction mode was the installation as it is with the movement quality interaction, and another mode was where the physical model had random kind of behaviors. It still had behaviors that were part of the system, but they were triggered randomly, meaning that they didn't correspond to what the dancer was doing. And in this study, we gave the dancers questionnaires after each mode of interaction, and we did an explicitation of experience interview and run a bunch of statistical analysis on it. And the results are for the company, for the dancers that are extreme experts of that vocabulary. For them, the visual behavior in the interactive mode responded clearly to their performed quality, and they saw the visuals are being alive, meaning that they had some kind of agency that was interesting for them. However, in the random mode, it was interesting that the dancer started imitating the behavior of the physical model as if it was some kind of teacher having its own agency and creating its own behavior that they would take on. For the student side, the interactive mode allowed them to have a better understanding of what double skin, double mind movement qualities were about, and a better experience of the installation as such. But again, just like the expert dancers, the behavior in the random mode influenced their movement in an interesting way, meaning that it allowed them to generate some kind of movements that they were not necessarily doing or going to do. So, still have a minute as a synthesis of the results and 4 minutes before the alarm. The visual behavior is a reflexive feedback, and that kind of movement quality interaction enhances the understanding of movement qualities for dancers and the user experience in an interactive system such as the one we designed. But randomness is not necessarily that negative, meaning that it leads to creating behaviors that could be interesting for a dancer to imitate in a pedagogical environment. And last, the contribution of that kind of work is to validate the concept of movement quality as an interaction modality in HCI, digital art, and dance, of course, but also experimental results that establish the correspondence between a visual behavior and movement qualities of a human body. I'd like to thank you and leave you with a video of the installation if you can see something. Thank you, and I'm taking questions.
Questions? Okay, I'm going to ask one. So you said that actually the dancers trying to imitate whatever they see, right? So are you, the dancers see this in action or afterwards?
They see the
visual, right? The visuals. So the
visuals are interactive, meaning they're dancing.
They're dancing. They're seeing it in the
yeah.
real time, right?
Yeah.
So, wow,
yeah,
they still can pay attention to it. Okay, it's amazing. Okay. Other questions? No, actually, we are finished on time before our alarm. Thank you very much. Just thank all the speakers for this.